So konsepnya just macam chit-chat lah Chit-chat, betul saya tunjuk lah sikit a few pictures.
So marilah kita bermula. Okay, so Madangkan tak ada masalah hari ni, so kita bolehlah cakap bahasa campur.
Okay.
Sebab minggu lepas ada foreigner lah. Sebab ada foreigner, so kita ada
okay, alright, okay.
Okay, so Assalamualaikum warahmatullahi wabarakatuh dan selamat petang. Jadi hari ini kita akan continue dengan kita punya physics topic talk, and this week the topic is introduction to solar photovoltaics.
Okay,
so without wasting our time, marilah kita mulakan. So doktor mungkin boleh bagi perkenalan apa itu solar photovoltaics. So kami basically tak semua daripada solar photovoltaic kan.
Okay, alright.
Get the idea dulu.
Okay, alright. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh to everybody. First of all, thanks for the invitation. So it's a good avenue for us to chit chat, discuss, have some ideas of physics. So this is that's why it's interesting. So I'm going to be sharing with you about solar photovoltaics. So before that, I would like to probably share to you a little bit of some backgrounds. I was actually an engineering student. So I graduated from electrical engineering during my degree. Okay. Then I worked for about 8 years altogether in industry. So after coming back from the UK, I spent about 8 years, 6.5 in Siltera. So if you have heard of Siltera Malaysia, Kulim High Tech. So I was in Siltera for 6.5 years. So I was a photolithography engineer. So if you have heard of photolithography process in semiconductor fabrication. And then I decided to continue my masters in physics, because along the way, a couple of years down the road, I found out that I would like to continue my career in semiconductor. And eventually, when I graduated last time, I planned to be an academician, but then I don't want to go right away into academician, so I just spent a couple of years to get the real hands-on experience in the field. So even though I graduated from electrical engineering, I really love semiconductor. So I think if you want to pursue your higher degrees, your masters, a PhD in something, in some field, in some topic, you better do something that you really love to do, because the journey is hard. Some of you are doing research, so you are really aware of how the research looks like, the up and down, and the challenges, difficulties. If the students ask me how easy is research, I can easily tell them, if you run 10 experiments, your success rate is only about 20%. If you run 10, you get only 2%. 2 out of 10 will be successful, and the other 8 will be something that you have to learn from. So in other words, I'll call that failure rate. So if you want to do higher degrees, you better do something that you really love. Whenever you are down, you collapse, no results, samples bad, you're ready to bounce back anytime. So that's why it's a must actually for me to do something that you really like. And don't simply do because there are some scholarships, the lecturer is nice, lecturer is kind, easy to give marks. It's not about that. It's about doing what you like. And then lecturers in the field will be your challenges, whether you like it or it's hard, or lecturers are strict or not really helpful. So those are the challenges that you have to face and you have to learn from in order to be a better student. Okay, so some introduction with that, and then I'm going to be talking about a few things. First of all, what is solar photovoltaics? Okay, so the students who have joined my class in 386, Semiconductor Physics and Devices, but none of you. Oh yeah, you're the one. Yes, you're the one. So you might be familiar with the content that I'm talking about, because you have learned and you have heard about some of the points. And then what is photovoltaic effect? So why do we call it photovoltaic? Okay, and then how does a solar cell operate? What is a solar cell, by the way? How does it operate? And then in order to generate current, what has to happen? Probably I can stop here and pass the mic to my student. All right, okay. That was just a few weeks away, right? So it should still be fresh in your mind. Baru class, okay? And then the device structure, how does it look like? And then the latest research progress in photovoltaics around the world. And then the efficiency of photovoltaics or solar panels. You know, when we talk about solar panels, you talk about efficiency, how much is the cost, and those are the important stuff, efficiency and cost. And then PV manufacturing in Malaysia. So how's the situation look like? Because you know, after your research, after your degree, you might want to end up in solar company or something. Might want to do research in solar cells, photovoltaics, or at a panel level. Okay. So first of all, why solar? So perhaps you can answer. Why solar? Why solar? Of all the energies, of all the renewable energies, why solar? First of all, the sun is abundant. The sun will be here until? Yes, until the doomsday, until hari kiamat, right? So it won't end. So if there's no more sun, means it's very soon, right? And then it's clean. So there's no pollution, there's no gas emission, okay? It's very clean energy. And then no moving parts. So if you see the solar panels, it's not moving. Even though some system they use tracking system in order to track the location of the sun, position of the sun, in order to maximize the photocurrent and voltage. So, but it's minimal, and then it's also reliable. The solar panel, if you base on silicon solar cells, they normally last for about 25 to 30 years. So whenever you invest in a PV system, you can trust in the system for the next 25 to 30 years. Okay, unless if you go for thin film cells, low cost system, then it'll probably last about 5 to 7 years. So it depends. So yeah, let me show you the solar spectrum. This is our solar spectrum. So you've been seeing at the sun every day, right? So this is the spectrum. If you want to see the wavelength, so the wavelength ranges from about 200, 300 down to about 2 micron. But the maximum power is at 600 nanometer. So that's the maximum power. So that's where the number of photons are the greatest. So it's equal to, if you equate that to band gap energy, so that will be equal to about 1.3 to 1.4 electron volts. So can you recall any semiconductors with 1.3, 1.4 or 1 point something electron volt? Silicon, right? Silicon 1.1, cadmium telluride 1.3, 1.4, indium phosphide 1.4, gallium arsenide 1.4. So if you want to have a solar cell, you have to choose the material with the right band gap. Okay, with the peak powers, because our peak power is at 600 nanometer, which corresponds to about 1.4 electron volt. You don't want to choose band gap that is equal to here, because the power is not so much. So you want to harvest from the maximum peak, right? So you want to harvest from the peak. So you have to align a band gap, because it's going to affect the absorption process. So I'm going to tell you later. So how far do you know PV manufacturing in Malaysia? How good do you know? Yeah, you know the companies? Jinko Solar, what else?
Because I know solar cells quite popular in Malaysia.
Yeah, actually we have all the giant companies in Malaysia. Yeah? Micron is probably doing wafers alone. Probably doing wafers alone, because some are doing wafers alone and then supplying to the PV panel company, PV manufacturing company. So in the world we are 4th largest. So we used to be number 3 last time. So based on 2016 we are number 4 in the world, PV manufacturing. But in terms of the usage, local usage, we are still very low. But then in the world we are number 4. So I've got the trend as well, I've shown in the class last time, right? So the first one is China. China is way up here. If you look at the market share against a number of years or a year, so market share of China is nearly 60% of the world market. China is up here, Then the second one is Taiwan, and then we are near to Japan and Malaysia. So we are number 4. So if you talk about Penang and Kulim, we have First Solar in Kulim, we have Panasonic Energy in Kulim, we have JA Solar in Penang, Bayalapas, we have Jinko Solar in Prai, and then we also have Hanwha Q Cells in Cyberjaya, Sun Power in Melaka, TS Solar Tech Bukit Minyak. Yeah, we have all the giants here. So that's why it should be, the awareness should be high already, because we have been number 3 and number 4 in the world. It's not only in this region, it's in the world. So we have various type of solar cells. We have monocrystalline, we have multicrystalline, we have thin film. But then in the manufacturing, almost 90% of the PV cells or solar cells are based on silicon wafers. So I bet you have all seen silicon wafers, right? So anybody haven't seen silicon wafers before? No, haven't seen, really? Okay, silicon wafer, normally the thickness is about 300 micron, 200 micron. Some use 300 micron or even higher. But the lowest in the market is now 200 micron or 180 micron, the minimum. Okay, so the technology based on silicon dominates about 90% of the PV market. So 90% of the solar panels that you're seeing in Malaysia or even in the world right now are based on silicon wafer, while the other 10% is based on cadmium telluride, like the one in First Solar, produced by First Solar in Kulim. Then some use amorphous silicon, some use cadmium telluride, some use copper indium gallium selenide, CIGS. Some also use CZTS, copper zinc tin sulfide. Okay, but 90% of those are based on silicon wafer. Okay, the idea of having both, why we have wafers and then why we have thin films, are actually due to the material consumption. Okay, if you look at the silicon wafers, the volume of material that we use is about 300 micron. So 300 micron is about 3 times thickness of your hair. So if you fool one hair, so the thickness is about 100 micron. So you times 3. Come on. So if you times 3, so it'll be equal to 300 micron, which is about the thickness of the silicon wafers used in the industry right now. Whereas when we start using silicon, then people realize that for monocrystalline silicon or single crystal silicon, the costs are very high because it's based on high energy intensive process and also laborious process. It's called Shogorowski process, CZAC process, or float zone, FZAC process, if you've heard before. So these processes are using high energy and then intensive and laborious as well. So at the same time using a high volume of material, which is about 300 micron. So in order to reduce the cost, I can show you later on, lesser and lesser amount of material has to be used. So instead of 300 micron of silicon, we need to reduce the amount of material to 10 micron, 20 micron, 2 micron, 1 micron, 100 nano, 500 nanos. But then it comes at a cost. If you look at silicon is an indirect bandgap material, right? So the absorption is not so good. So indirectly you can say silicon has a poor absorption. That's why it needs a very thick amount of material in order to absorb most of the incident light. But then some of the materials like cadmium telluride, gallium arsenide, what else? Amorphous silicon even, they are direct bandgap materials. So since they are direct bandgap materials, so they don't really need thick amount of material in order to fully absorb the sunlight. So amount of 2 micron, 3 micron will do already in order to absorb. So just compare the amount. 2 micron of cadmium telluride, like the one being used in First Solar right now in Kulim, compared to 200 to 300 micron of silicon, which dominates 90% of PV market. So the amount is like 150 threshold, 150 fold difference. So such a big amount. But then silicon has a good reputation. Silicon has good efficiency and good reliability as well. Whereas for thin films, there are a couple of issues still need to be addressed. I can show you later on. Okay. But before that, let me just remind you of the photovoltaic effect. So anybody aware of photovoltaic effect? Okay. So it's the creation of voltage or correspondingly current, electric current in the material upon exposure to electromagnetic radiation. So in this case, sunlight. So three things has to happen whenever you put a solar cell under sunlight. First thing is the solar cell has to absorb the light. So in order to absorb, the energy of the incident photons has to be equal to or more than the band gap of the material. Okay. So whenever the light is absorbed or the photons are absorbed, photons are of high energy, okay, then the band gap, and then it will create electron and hole pairs. We call it photogeneration. So first light is absorbed or incident photons are absorbed, and then electron and hole pairs are created. Electron is excited to conduction band, hole stays in valence band, and then we have p-n junction at the same time. So p-n junction will try to separate the carriers into two different directions. So electron goes to n-type, holes go to p-type, and then both of them are carrying will be extracted by the electric circuit, by the external circuit, and then we have IV curve. So that's the basic. So yeah, it looks pretty much like this. This is just a schematic, by the way. So a typical solar cell, so let's just assume this is silicon. So we'll have a base material which will consume about 99 or 95% of the whole thickness of the material. So if you assume the silicon wafer is about 300 micron, so usually 299.5 micron is used as the base. So the typical one in the industry is usually using p-type. Some are using n-type. Okay, only the front side use a very thin layer of emitter, usually about 200 nanometers or 300 nanometers. And then we have front contact and rear contact for the p-n junction, right? To extract the electron and holes. And then we also have anti-reflection coating, ARC, anti-reflective coating. Because in the solar cell, we want to minimize as much reflection as possible. So I've told you in the class that absorption is equal to 100% minus reflection minus transmission. Okay, so since the wafer is opaque, so there is no transmission through the wafer. So that means A is equal to 1 minus R. So if you can minimize the R, or the amount of light reflected back into the ambient or into the atmosphere, so that means you can maximize your absorption. So one way to reduce the reflection is by having one anti-reflective coating. So normally for silicon, we use silicon nitride in the industry. So the thickness is usually about 75 nanometers to 80 nanometers, hardly exceed 100 nanometers, so a very thin layer. So the way it operates is by destructive interference effect. So it will destructively control the interference between incident and reflected light, so that the effective reflection is zero. Okay. So if you want to know, the first modern silicon solar cell was fabricated back in 1954. So yeah, long time ago, right? Yeah, at that particular time the efficiency was 6%. Okay, fabricated in Bell Lab. Okay, Bell Telephone Lab. Okay, but then it was the enthusiasm to fabricate solar cell was very high at that time, but then it was slowly dampened due to immaturity of the silicon preparation industry. Because in order for you to fabricate a good high efficiency solar cell, you have to have good wafers. So if the silicon industry is not really prepared, or the impurity is not good, the cost is high, the efficiency is not so good of the wafers itself, so you won't be able to produce a high efficiency solar cells. So okay, the next one, let's just look at the generation of the photovoltaic cell. Actually in the field we have 3 generations. We call it Gen 1, Gen 2, Gen 3. So I've also prepared for you this diagram. So this is Gen 1, the green one. Gen 2 is the yellow one, small one. Gen 3 is the red one. Okay, Gen 1 is also known as the silicon or wafer based solar cell. So whatever you see on the roof right now is mostly Gen 1, so generation 1. But people who are doing silicon or PV research, they normally categorize other researchers or other students by generation. So you're from Gen 1 or Gen 2 or Gen 3, something like that. So if you do thin films, amorphous silicon, for example, so you're from Gen 2, you're working on monocrystalline, multicrystalline wafers, you're from Gen 1, so you're normally categorized by generation. Okay, generation 1 is here. You can see efficiency versus cost curve. So for generation 1, we have monocrystalline wafers or single crystal wafers that we normally see in our lab. We can't see any grains, right? So there's no visible grains. So the other type of wafers is multicrystalline, so also heavily used in solar industry. So they are wafers where you can see all the grains. The grains are visible, the grains are very big. If you see 15 by 15 centimeter of silicon wafer used on PV panel, so you can clearly see the grains. Normally about 5 centimeter, 6 centimeter long width. So about there you can see the grains clearly. So the efficiency is about 16 to 25 roughly. If you use multicrystalline, those with grains, the efficiency ranges from 16 to 20%. Whereas if you use single crystal, the efficiency is about 20 to 24, 25. Currently the world record is being held by University of New South Wales. So the lab scale efficiency is about 25 point something percent back in 1998. So then researchers are trying to, working ways to reduce costs. So the people are starting to think, why do we reduce the volume of material? Then we have generation 2, where we reduce the amount of material significantly from 300 micron to 200 to 300 micron to only about 1 micron, 2 micron. Then we have thin film silicon. So previously we have silicon wafers, then we already have thin film. So the efficiency is slightly lower, usually from 8 to 15, but then the cost is also lower. So this generation are targeting different market niche. So panel based on silicon are having their own market niche, and while thin film are having their own market niche as well. So they don't disturb each other. And then from the second generation, researchers are trying to improve further. Okay, they say, why don't we use thin film and then try to improve the efficiency further? And then we have all the new materials like organic solar cells, perovskite solar cells, latest one, perovskite, which is based on hybrid design architecture within organic and inorganic. So the latest efficiency was just reached a few days back, up to 22.1, if I'm not mistaken, with stable efficiency. So altogether we have 3 generations of solar cells. This is the one that I told you now. So we have mono. So if you have mono, then you see nothing. You don't see the grains. So you see very clearly. Everything is just clean surface. And then while multi, you can see the grains, right? Even from there you can see different colors, right? So the grains are of different colors. So the grains are what we call strategic place for electron and hole to recombine. So if you learn device physics, once you have created the electron and hole pairs from the incident photons, they'll travel along the way through the emitter, through the absorber, to go to the front contact and rear contact. And along the way, if they find the grain boundaries, if they collide with the grain boundaries, they'll recombine due to the defects, because grain boundaries are defects. So we don't want to have grain boundaries. But then, since multicrystalline wafers are much cheaper compared to monocrystalline, so researchers are trying to fabricate good solar cells on multicrystalline wafers. And they have a couple of techniques in order to fix the grain boundary defects, like surface preservation and so on and so forth. You must still remember, right, in the class? Surface preservation and bulk preservation. Okay, let's go to thin film. These are the examples of thin films. We have cadmium telluride. This is currently being manufactured by First Solar in Kulim. So the highest efficiency is about 16 to 17% module efficiency, module size. If lab scale sample, they have produced in the US, I think a few years back, up to 21%. But then if you upscale, you'll have more resistive losses, more recombination, more so on and so forth. Then we have lower amount of efficiency. Then we also have organic solar cells, which can easily be printed by printing process or roll-to-roll process, okay, on plastic, on fabric. Then we also have perovskite solar cells. This is pretty new. They started on the research on perovskite started in 2009 or 2010. But then the efficiency is almost equal to silicon right now. So the silicon, since 1954, the first one was only 60%, right? And then now it's been 40 years, more than 40 years. So it's only 25. So perovskite started in 2009 with 4% efficiency, currently 22. So the rapid increase in efficiency is very fast, because The material itself is interesting, and it doesn't require vacuum processing as well, so you can just thermally evaporate or spin coat even. So you don't really need high-tech equipment, in order to produce good quality. Then when I was in a conference last time, 2014 in Kyoto, and then one research institute, they presented their finding on perovskite. They showed a picture of the cell. The picture was very ugly, but then the IV curve is very amazing. So you don't really have to have a very, good-looking solar cell for it to be good. So yeah, for perovskite. But for silicon, if you have that kind of solar cell, gone. You probably can't even produce 0.1%. So perovskite is very robust. So they say it's very robust. Even though it looks ugly, performance is very good. So that's one of the advantages. So many researchers and so many scientists around the world are starting to work on perovskite, and we have so many papers, month by month on perovskite solar cells. And we also have CZTS solar cell, copper zinc tin sulfide solar cells. Currently the highest efficiency is about 8%, also by UNSW. So in UNSW last time we have a very big team, about 20 students if I'm not mistaken, working on CZTS solar cell alone. Last time I graduated from UNSW, so in the school, there are a couple of groups working on different types of solar cells. One group working on Gen 1 alone, so we have like 20 students working on silicon solar cells, mono and multi. And then Gen 2 we have about 5 to 10 students working on thin film silicon solar cells. And then we have perovskite, we have organic, we have CZTS as well, with so many number of students. But right now, I believe the highest number of students belongs to perovskite solar cells. Because they are even trying to use perovskite solar cell on top of silicon, on tandem architecture, in order to reach the silicon efficiency of about 30%. Because silicon, the band gap is 1.1 electron volt, the theoretical efficiency for single junction solar cell is about 29 to 30%. To be exact, I think 29.1. So that's the ceiling that you can hit. So currently the lab scale is already about 26%. So only 3% left in order for all the improvement in the world to hit. So the ceiling is almost there for silicon. So people are trying to put on another architecture like tandem in order to push beyond the efficiency limit. Okay, if you look at the schematic as well, you can see usually solar cell, in order to minimize the reflection, the surface is usually not planar. We normally either have pyramids on top due to the anisotropic etching, if you learned about anisotropic etching before. So if you use silicon of 111 orientation, and then you use KOH or sodium hydroxide, you automatically get pyramids. The size is about 3 to 5 micron usually. Okay, so that's why this one is the most popular one for monocrystalline wafers. But on multicrystalline wafers, you cannot get pyramid because the etching will be isotropic or will be equal in all direction. So the etch rate will be almost equal in all direction. But this one will have selective etch rate for different planes. So for monocrystalline or multicrystalline, you will normally end up as pores, macam lubang, instead of having pyramids. So you have to have this kind of surface before you put the ARC on. Okay, just now remember ARC, anti-reflective coating. So if you don't have pyramids or pores, if you have just a plain surface, you put ARC is just a waste. The reflection will still be very high. Because the theory says the refractive index of silicon is about 3.6 at 600 nanometers. So that is equal to 33% of reflection at that particular wavelength. So that means out of your 100% of your incident photons, 33% of the incident photons will be reflected back to the ambient. So you only have 67% to play with, to absorb. So 30% is already lost, reflection loss we call it. So in order to minimize the 30%, you have to texture the surface. We call it surface texturing. Surface texturing, you can reduce the reflection from 33% to theoretically down to about 11% on monocrystalline, or theoretically down to 22% for multicrystalline without ARC. Okay, so 11% at 600. So you still have 11% of reflection loss compared to previously 33%. So in order to minimize further the 11%, you have to put the ARC on. So they put the ARC on, it will suppress the reflection at a specific wavelength, usually at 600 because that's the peak of our solar power. So it will suppress to near zero. So the reflection will be a bit high in the blue region, close to zero at the 600, and then goes back high again. That's why just now when I showed you the wafer, it looks a bit bluish. That's because you have reflectivity at the blue region. That's why the color is blue. It's not because of the color of the gases or layer. It's the real reflection at that wavelength. Okay, that's why it is seen as blue. So yeah, you have to have pyramids. Then you put ARC on. Then you have your front contact. You have your rear contact. Then you have a complete solar cell already. Okay, the latest. Let me share with you the latest R&D in PV research. Currently, March 2017, just last month. Normally, I keep following all the updates because I want to do the latest research. So, Kaneka Corporation, one company, is hitting 26.3% of conversion efficiency for silicon wafers. So, can you see the color right now? What's the color of the wafer? It's black, right? So, why is it black? So, it completely absorbed. Or perhaps reflection is 0.1% left. The rest are completely absorbed. So you go back to A equals to 1 minus R. When R is close to 0, A is close to 100. Easy. So whenever you have your surface black, you will have a very high photocurrent. So they've hit up to 26.3%. So that means out of 29.1% theoretical limit, only 2.8% efficiency to be improved. Then once you hit 29.1, you're done with silicon. And we have to work on something else, or silicon in combination with something else. Okay, so this device uses monocrystalline wafer on only 165 micron of absorber thickness. So that's about 1.5 thickness of your hair. So hair is about 100 microns, so times 1.5 is about 150, 160. So only that thickness of material that we use in order to get 26.3. So yeah, use heterojunction design, interdigitated back contact. This one is all a specific design concept that companies and researchers are trying to do around the world in order to hit as maximum as possible. And then on perovskite as well, yeah, this one that I mentioned now. Just a few days back, I think. Yeah, a few days back. 21.2% efficiency of perovskite solar cell with stable efficiency. One of the problem of perovskite solar cell is it can heat up to 21, 22, but then after a couple of hours of sun exposure, the efficiency can drop down to 10%. So now on perovskite, chemists and organic solar cell researchers are trying to improve the stability of the material. So they are playing with organic material and hybrid material, different kind of dopant, different kind of donor materials, and different architecture in order to have a very stable efficiency over long hours. So the standard is about 1,000 hours of light exposure for you to say that it's good enough to be commercialized. So they've hit 21.2 from Korea University. Distinguished Professor Sang Seo in March, just a few days back. Okay, just 2 weeks back. So now, yeah, attention is going to perovskite. So let me show you the graph. This is being tracked by my previous university, UNSW. So you can see the silicon. This is only from January this year. January 2013 until January 2017, because that's when perovskite started. So in 2013, or not 2009, 2013, it was only about 10 or close to 14, 15. Then it's up to 20 something already. So it's closing the gap with silicon at 26.6. Okay. So whenever you go to, if you do solar cells research, you go to solar conference, they'll present to you all the efficiency map. Where's the current point? This year was the current point, probably just 2 days back with new efficiency limit or something, new efficiency on. This is the other one I've shown in the class last time. UNSW, my previous university, has just got 2.5 million Aussie dollar of Australian government grant for perovskite commercialization. So they try to commercialize perovskite. So for solar cell to be commercially viable, they have to hit 15% of efficiency. So then only if you're still evaluating in the range of 12, 13, 10 or even lower than 10, no room for commercialization. So you have to hit 15, prove that it is stable over a long period of time, then you're ready for commercialization. Provided somebody want to invest. In Malaysia, I'm not sure at the moment. You might have to wait for a couple of years. So this is the standard efficiency map. So many points due to so many technologies invented by so many research institutions and universities around the world. So if you see different colors, it belongs to different technology. Some is on silicon, some is on mono, some multi, some thin film, some 3,5, gallium arsenide, some nitride, some with the lens, concentrated technology. So many technologies, but then it's being maintained by NREL in the US, Colorado, National Renewable Energy Laboratory in Colorado, Golden, Colorado. So every time people go to big solar conference, they'll present this graph. So that people will see, oh, our latest point is here, latest point is here. So it's not moving. This technology is just stagnant. Probably no more chance for improvement, no more funding. And the big funder also look at this. If they see a very high increase in the gradient, or the gradient is steeper compared to other technologies, they'll probably look into that technology for investment. If you look at something that stagnant since 1995, probably just forget about it, apply for new grants, do different materials and stuff. So there is kind of an indicator or signal for researchers and scientists and even manufacturers as well to invest. So this is what I mentioned now, all the companies in Malaysia. So we have First Solar in Kulim, Panasonic in Kulim as well, Jinko Prai, JA Bayan Lepas, Hanwha QCell, Cyberjaya, Sun Power Melaka, and TS Solar Tech, just Juru, Auto City. So we have all the giants here. I think all the top 5. Yeah, top 5. And we also have PV manufacturer ranking. So the first one in the world is right now GCL from China, if I'm not mistaken. Second, Trina Solar, China. Third one, Jinko Solar, China. Fourth one, JA Solar, China. Wacker, I'm not sure. Wacker is currently number 5. Hanwha is Korean. Canadian Solar, Canada. OCI, I'm not sure. First Solar is from the US. So yeah, top 3, top 5 currently being nominated by China. So they have a huge investment, very huge investment in terms of research, manufacturing, number of students around the world. If you go everywhere, you can see Chinese students from mainland China, right? You've seen the US, I've seen in the Australia, UK. Yeah, they're everywhere. They're investing in the education, research, manufacturing, and everything. So you don't be surprised in the next few years, top 10 all China. That's possible due to the huge investment. So yeah, that's pretty much what I have to say. So if you have questions or suggestions or any points you want to share.
So how about the synthesized solar cell?
That synthesized solar cell, the efficiency is still very low. As far as I'm concerned, it's still below 10%. I'm still seeing some papers being published in good journals with only 1% efficiency. So that means the efficiency of the overall technology is not very high. So that's why it is still publishable. And I believe it's also have stability issues as well. So yeah. Some people are still working on organic and DSSC with the hope that it can hit 10%. But the bottom line is if you can't hit 15, no room. Yeah, any more question or anything else? Alright, okay.
What's the current technology on 3 nitride-based solar cell? I know it's still a bit behind the silicon.
Okay. Yeah, nitride is currently being researched by US scientists, but only in multi-junction. So that means you have to have a very high band gap on top as your first cell or top cell, we normally call it top cell and bottom cell. Top cell has to have, if you use tandem, means 2 cell, you have to use some material in between 2 to 2.5 electron volt as your top cell, and then below 1 or near to 1 as your bottom cell. So currently the direction is going for about 40%. 3.5 they want to go to 40% or above. So currently I think it's still low, and not many researchers are doing 3.5 because one, it is expensive, and then it's more for space cell, and then more for concentrated system with the lens, with the huge lens. So with the huge lens, the investment has to be very huge, and then you have to have a very big field to accommodate big lens, big panels. Then yeah, that's why people are not many researchers are working on 3.5. But of course there are rooms to play, there are rooms to improve, and yeah. In general, most people currently are working on silicon, mono and multi, silicon tandem, silicon plus something else, silicon plus CCTS, silicon plus perovskite, and then perovskite alone, and then cadmium telluride. Those are the main hot areas in PV currently, at the moment.
I want to ask a question on the consumer point of view.
Okay.
So, as a consumer, is it good time to invest on applying solar cell to our home or right now, or is it we are on the verge of maybe a breakthrough in solar cell technology? So,
To say it's a good time in Malaysia, in context of Malaysia, it's not a very good time. It's not discouraging, but then the government has just switched from feed-in tariff to net energy metering technique. The way they feed you back because if you have a solar panel on your roof, they can either be off-grid, that means you use on your own, so there's no connection to the grid at all, or the other one will be on-grid or grid connected, where you generate, and then if you have excess, you can sell to TNB. Okay, that's the model that people are using around the world, but not very much in Malaysia. You can either go off-grid or on-grid. The beauty of having grid connected is if you have excess of energy, you say if you have a large amount of roof, and then you can accommodate a lot of panels, and then the energy that you generate is much more than what you consume. Well, the typical household is about 3 to 5 kilowatt per household usually, so 3 to 5 kilowatt. So the way to calculate is you look at your bills. Okay, say you use a few hundreds of kilowatt hour per month, and you divide by number of days per month, which is 30 roughly. So then you have kilowatt hour per day, and then you divide by number of sun exposure per day, which is roughly 3 to 5. But people are using average of 4, so divide by 4, then you have your household use for every day. So from there you can scale your panel in order to be under design compared to your consumption, or to over design compared to your consumption. If you over design, means you will have excess energy from your panel, well, you can sell back to TNB and they'll pay you money. But then situation in Malaysia, as far as I'm concerned, is not very encouraging, because TNB is the only dominant energy supplier. If you go to overseas, Australia, UK, US, there are a couple of energy suppliers you can choose based on healthy competition. But in Malaysia, we have a sole dominant of suppliers, so we don't have much to say from consumers' point of view. So if you have different kind of suppliers, then they'll offer you different rates, and then which one is the most encouraging one, they you can adopt to the system, go grid connected, supply extra, then they can pay you back. So that's what's happening in Europe and even in Australia. If people in Australia, people are using about 3 to 5 kilowatt, and the ROI of the system, return on investment or balik modal in system, is about 3 to 5 years if you use silicon panel. So after 5 years, it's totally on your own. So you're generating on your own. So you're basically an IPP, independent power producer. So the system can last for about 20 years, 25 years. So that means after 5 years, for the next 15 to 20 years, it's your money. Yeah, pretty much you can say that. Yeah, pretty much you can say that. Yes. So, but in Malaysia, the situation is a bit different. I heard that with NEM, it's even more than 7 years. So I'm not sure exactly how much. It probably is dependent on the size of the solar panel as well. So I heard that it's more than 7 years. But with the new system, we call it NEM or net energy metering. I heard that it's not as encouraging as before. So that means it should be more than that. Perhaps 10. I don't know exactly. But the idea is if the panel can last up to 20-25 years. So worst case, if your ROI is 10 years, so the next 10 years will be yours. So the government just switched to NEM from feed-in tariff or FIT to NEM just early of this year because they want to encourage people to use renewable energy last few years, and then probably they have seen sufficient amount of renewable energy, even though it's not really sufficient if you see the roadmap. Then they start reducing the amount of subsidy that we can have. So that's basically amount of subsidy. If you increase your ROI from 5 to 7, so you're losing your subsidy already. So they're going into that direction to reduce further and further. But hopefully, if the future is brighter than what we are in now, hopefully it can be revised, or it can be more encouraging, or probably as encouraging as before. FIT. I hope so. So that's the idea. The ROI in Malaysia is still quite long. Now 6. So any more question, or if you want to talk about solar cell research, or if you're interested to know more, just come and knock on my door, 205. I'm all good. I'll be doing all the solar cell research in my career. I'll be devoting my life towards solar cells. Inshallah. Inshallah. Okay. Yeah. Yeah.
In the structure of solar cell,
Yep.
it does have TCO, right?
Yep. Conductive, yeah.
So, what is the current material used and what is the factor you consider?
Okay. If you see transparent conductive oxide, I've shown the structure in the class. They should remember. You should actually consult them though. Transparent conductive oxide has to fulfill 2 criteria. It has to be transparent and it has to be conductive at the same time. Okay. So TCO is one example of degenerate semiconductors. So if you've learned about degenerate semiconductors, the doping level is very high. Usually it's high 10 to the power of 19 or early 10 to the power of 20. So the usual material is ITO. So ITO, so indium tin oxide. So in solar cells, it doesn't have to be TCO only. It can be, like silicon nitride. It's not a TCO. It's not conductive, but then it serves as a good optical layer. But then if it can be conductive, it's even better. Because whenever you see the solar cell structure, the emitter has to be as conductive as possible. So in order to increase the conductivity, the emitter, the red one, has to be as conductive as possible. So that means if you use silicon, if you diffuse junction, you have to diffuse a very high doping level of phosphorus or boron. If you want to have N-type, then use emitter phosphorus. For N-type, then you have to go about high 19, 510 to the power 19 in order to have a low enough series resistance. So on the other hand, you can also use TCO on top in order to further boost the conductivity of the emitter. So the lateral conduction will be improved. So you don't want to dope the emitter too high because you'll increase the recombination. So the layer that you dope with high level of 1019 will be a dead layer, practically a dead layer. So not much electron can be collected from this layer. Only small amount of material. If you see quantum efficiency curve, you can see the amount of collection is very small from this region. So that's why researchers are using a TCO in order to improve the lateral conductivity. But then it's not a must. It's good, but it's not a must. So it has to be transparent. Transparent means transmission has to be higher than 90%, or worst case 85. If you have below 85, forget about it. Or conductivity has to be very good. in the range of 10 to 20 ohm per square. The thickness has to be only about 80 nanometers, 100 nanometers. Cannot be very thick, or else you have a high parasitic absorption in the layer. You don't want to absorb in the layer. You want the light to pass through to the absorber, to the silicon.
It's absorbed, right?
Yes, so it has to allow as much light as possible through the TCO. That's why the transmission has to be high. If you have 80, 85, that means some amount of the light already absorbed in the TCO or reflected by the TCO. So it has to be transparent, conductive. Transmission higher than 90%, conductivity 10 to 20 ohm per square. Usually. But it's not a must. It can be silicon nitride, it can be zinc oxide, it can be silicon dioxide, as long as it fulfills the optical layer requirement. There's other requirements, long one, equations and thickness and so many other things. Yeah, so everything is clear?
So thank you, Doctor.
Okay.
So thank you for the session today. So we'll be continuing the next coffee talk same time next week on Wednesday 5 p.m. The speaker is not yet confirmed.
Alright, okay, thank you very much for your attendance. Thank you. Assalamualaikum.
No.